So friends, we are into our last lecture of week 5, and here again we came back to major elements and function in integrated simulation. So we will have a look at our what we expect, what are the modules that are available. Plant PRA modeling is central to our this thing system, and integrated simulation is the objective here. Okay, for risk simulation, development stage of PRA model. That means we have the PRA and we have the cut sets available, and these cut sets will form part of the risk monitor. Okay, and then Monte Carlo simulation for uncertainty analysis. We know that we have discussed this, and this same Monte Carlo simulation which is giving us uncertainty estimate becomes useful for sensitivity analysis, be it uncertainty band, be it assumption or data, its impact, and even if the component failure probability data itself absolute, that point value we can check it. So uncertainty and sensitivity analysis are very important part of PRA modeling. Now when we come to risk monitor, the risk monitor model is basically simulation of finalizing list of cut sets from PRA, which form input to the risk monitor, finalizing the cut set list and associated uncertainty in parameter. Okay, and common cause and human factor requires a special attention in adopting any PRA model into risk monitor, because a grouping has to be made for reflecting appropriately the consideration of common cause failure. That is one thing, and uncertainty also or human factor data also has to be seen in variability, because uncertainty is higher. So it should not what data we should expect and what data we should not expect, what uncertainty level we should expect or what uncertainty level we should not expect, because beyond certain limit, if it is a wider uncertainty level, then the information itself becomes not available. So we have to work on that and collect more and more data for a risk monitor. Simulation for specific aspect like technical specification, then plant shutdown, maintenance management. These are the functions that we can see we want to realize in our risk monitor or as part of risk informed risk based regulation. And simulation of emergency scenario, that happens in the plant simulator, and from there whatever data we collect and insight we collect, it has to be seen in an integrated way on the risk monitor and control room scenario to have a better feel of the one time accident, or the accident don't happen sometime, but preparedness is required at human level, at component level also. So these insights will be very useful, and the good part is to run this simulation on anticipated occurrences, that is loss of upside power and all that, so that we'll come to know how our simulator is adequately representing our risk model, how our risk monitor itself is representing our model, and how human factor considerations have been embedded into the risk model. Okay, so integrated approach to simulation, as we have discussed, integrated risk simulation and safety insights, that is our objective. Okay, so and how we get it, at the core is a PRA study, and PRA study form the basis for risk monitor. So and risk monitor, what it does, operations and O&M decisions, and failure, it gives input to insight into the IRS. And then plant simulator provides input on human factor and various plant configuration that we choose, as I mentioned, the deterministic part, deterministic. Okay, and then AI/ML advisory approach. If there is a advisory system. So there is a mode of communication between PRA model, risk monitor, plant simulator, and operator advisory system, because finally it forms a closed loop by operator action. Okay, so corrective action program can be implemented through this advisory system. So for a holistic and integrated simulation, we have to have these 4 elements in place, wherein the PRA is the fundamental thing. Okay, so Monte Carlo simulation. What we do in Monte Carlo simulation, let's say for a fault tree. Now we have point value. We have obtained through cut set Boolean analysis. Okay, and we have reduced the fault tree also. Though that is also not easy when the fault trees are running into pages. Okay, but we have done sometimes. But then if you want uncertainty estimates in our final fault tree results, then a Monte Carlo simulation becomes a must. So that means fault tree reduction and Monte Carlo simulation, these things should go on together. What is Monte Carlo simulation? It does is define a distribution for component also. Okay, so for each component we'll provide the median value, because for the component which are coming from different source, they are assumed to follow log normal distribution. So that means for log normal distribution, median value has to be given and distribution has to be given. Okay, so this will enable estimation of main event, that is let us say if it is a emergency power supply or class 3 power supply failure. So uncertainty in the estimation also. So first step is define the mathematical formulation of the problem along. Basically this Monte Carlo simulation requires a computer programming. Okay, so a program has to be written, and now in a generic open sources this program must be available. So one can see that, but it is a computerized evaluation wherein first of all we have to define a mathematical formulation to. So my mathematical model is my cut set equation. Unavailability is equal to C1 into C2 plus C3 plus C common cause. So that will give us, unavailability equation will give us a mathematical formulation. Identification of the input parameter used in the formulation along with their appropriate probability distribution. So name of the distribution, then median value, and then distribution, what distribution it is following. And the most important step is random number. We have to have a routine for random number selection. So from that distribution, one random probability will be generated, and then so many iteration, 1000 iteration will be formed from top to bottom as part of the Monte Carlo simulation. And finally at every simulation there will be top probability will be reached by considering component or basic event failure probability. Since this was an old thing that computationally intensive and all that, but now that is not a problem. So Monte Carlo simulation, even though it is up to 1000 or 1200 or but minimum 1000 number of iterations are required. So you can for fine tuning the result we can go up to 5000, because now computers are very advanced actually. So we can go for that kind of a situation. So it is okay. And then presentation of result that include estimates of mean for objective function and uncertainty bound. Okay. So let's say we had this cut sets from our exercise. Diesel generator DG1 is the failure probability, and you see we have given the error factor. Error factor means I have defined here. Error factor is nothing but 95% limit divided by the median value. So generally, if we have a good confidence in our, let us say these are all our plant specific data, so we take an error factor of 3. If it is a human reliability, error factor of 5, because data and all. Common cause failure, further it will be because data is not available on common cause failure. So it will be 5, sometimes for certain components or certain where there are no failure, it will be more than 5 also. But wherever we have confidence, so generally a value of 3, but we can estimate ourselves whatever. So we have assigned a log normal distribution. You can see for each component, log normal distribution 95% bounds we have given, and then error factor. So we have simply given error factors here. Okay, this is just I am saying this is a median value, and this is 95%. For all the components we have characterized, so finally the output of class 3 or emergency power failure will be a distribution 95%, median value 95% value and 5% value, but basically we want upper bounds only, because lower bounds may not require. So 95% value and this one. So that becomes uncertainty estimate on the required direction. So let us say class 3 power failure EPS is 3.23 into 10 to the minus 3, and upper bound is equal to will become actually 9.7 to 10 to the minus 3. Sorry, this is 95% bound, median value, and lower bound and upper. Upper bound is 9.7 and I have approximated it to 1 into 10 to the minus 2. So this is the 95% bound we get here actually. So this is uncertainty correction Monte Carlo simulation we have over here actually. Now plant simulator. Plant simulators are you can see there that employed for mainly for training. To the extent possible, credible postulated. Actually, plant simulator should be able to run session for most of the PIEs, postulated initiating event given in the safety report, but always it is not possible. So at least few credible accident sequences and few anticipated accident sequences we should be able to model it. Systems and component failure, we should be able to reflect there. Sessions are run by failing the component, what happens? So operator as part of training they understand what are the repercussions of any particular component failure or system failure. Objective is to reduce human error in real time plant. So once we do it and learn here, probably in the real time situation, if the same situation comes or similar situation comes, we are able to handle it better. And then plant simulators are there for development of human factor studies. In fact, development of a new model also is possible through simulator, because many experiments can be done only in the simulator room, like stress level of the operator, then seeing the plant response either visually, or this thing. So, and then even we can, so if we have a simulator and if we have operator support system interface to the simulator, and if you have a risk monitor also, it becomes a ecosystem for integrated simulation. Okay. So here we have a typical prototype risk monitor where risk characteristics are given here. Okay. And then on various dates, whatever the changes we have done and what are the plant configuration, which system we selected, and what kind of data we had changed here, and then simulation was performed to get the risk level. So risk monitors are basically application is risk monitoring either in the operation, maintenance, and in regulation if you want to check. Objective in operation environment in the context of configuration management, surveillance test interval estimation, all those things we can do some increase in risk, or we can plot our trend graphs here, and then because technical specification optimization is a stipulation, and if we want any change, we have to make a robust case. So we have to show the trend of increasing or decreasing risk for various metrics that we have selected for demonstration. Risk monitor and simulator are critical to evaluation of safety scenario for multi-objective option. When apart from risk, we want to have a plant operability also, risk also, and many quality related parameter, then it becomes a multi-objective function. So how to do that? That can be done in this integrated ecosystem. Change in risk is the basic function, and how plant performance changes in when it affects the process system also. Risk monitor and plant simulators provide a holistic platform to effectively simulation human response. In fact, the best thing is we can integrate, we can assess the human response on the simulator and show its impact on the risk monitor, and then if we have operator support system, or if we don't have that provision in operator support system, we can incorporate that and see what is the reduction in risk if we have that component which was not defined in operator support system. So this is the advantage of integrated simulation. And then okay, so we have a operator support system, advisory system, and usual what it does basically is plant transient. Actually one requires operator support system for two situations. One is when the plant transient occurs. The transient means from normal operation to shutdown. So this happens in a very short time, and for that you require a effective system. So here AI plays very important role, like artificial neural network, which has got the capacity to perform this procedure and process the signal in parallel and produce and identify the plant state. So that is one thing. Second thing is, when plant is shut down, scenario evolves very slowly, because the plant response now has to be seen. Emergency power supply has come or not. So which systems are operating, which systems are not operating, and what is the, so here operator can take a clue, but these are transients are automatic. Only thing is ANN helps in identifying the scenario, because human mind gets affected by certain scenarios, but computers have their own way of functioning. If the plant if the state was part of training in ANN or AI ML, then probably it will be easy to identify the transient, and this much time is saved for the operator to devote it for diagnostics, which is the following case. And then PRA based operator support system. Now for that, what we need, a operator support system also a PRA based. That means PRA knowledge should be used for developing the diagnostics. Okay. And there is one paper which discusses about this situation. Role of probabilistic risk assessment, we have discussed it. In ANN for machine learning, transient identification, event tree and fault tree for diagnostics and development of this thing. Two major function control room, that is state transient and identification. This can be done very well. And AI/ML operators, and given this scenario, now we have more advanced AI/ML algorithm, and we can do. And along with that, we have a human precursor analysis which can be done in simulator, and root cause analysis. To some extent, it can be done. In fact, some simulation can be formed for understanding the root cause. Provided the plant response, simulator response is similar to the plant response. Now, there are something operational precursor analysis. Okay, what we are saying here is that failures happen later on, and in fact, it is almost similar to prognostics. Okay, but symptoms are available. So symptoms are available. So some precursor studies, like some smell is coming in some room, so is it electrical failure or some vibration level increasing? Is it a precursor to a pump failure or any other failure? So this precursor study forms a very important part in PHM also, and as such in plant atmosphere administrative level also, or technical level also. So so that means if suppose we use a fault tree approach or event tree approach for defining these failures, then we will be able to have a list of precursors that leads to the top component failure, and that is where risk based engineering or risk informed engineering use it, or same thing even prognostics and health management also does. So this can be used for surveillance, monitoring, inspection, because we want to catch the precursor. So that means periodic rounds, sensors should be available to give us an advanced information before a component fails, or precursors are available. So generally, if any accident happens, so PRA model provides a very good framework for a precursor analysis. What would have been the root precursor for that failure? Same thing applies for the human root cause analysis. Generally, it has been seen that error of emission, omission, error of commission, and then lapse, and this thing. But then, if you look at the human root cause analysis fault tree, you will find that there is more to that and why human error occurred. You have to find out those questions. Not that these are the error of why error of omission has happened, why error of commission has happened, why mistake has happened. So those routes should be available. Directive framework should be available, and fault tree is a provides a very effective mechanism, and this has been dealt in one of my book actually on risk conscious operation management. Simulation experiments can be performed. Consideration of conscious cognition should be there for root cause analysis. So we should go to the root of conscious cognition. It is consciousness and cognition and conscience. Okay, conscience means security related issue. We will discuss in separately. Feedback and follow up to understand the benefits of, and QA program is in HRA is a must. Okay, and I think industry is putting a lot of efforts in that direction. So what is the we have seen integrated simulation approach, where the risk monitor, which is feasible through having a risk monitor, having simulator, plant simulator, and then along with that we have very good insight from risk confirmed risk based inspection also, and of course operator support system, which so plant intelligent operator support system is there. These four elements they form the, and then integrated simulation tends to support more effective decision making in collective information. So we have week 5 completed with this slide. Next we will meet in next lecture of risk conscious operation management for complex engineering system.